In this series of videos, we're actually going to extend our knowledge of A level and look at in more detail as to how atoms actually bond together to try and explain some of the odd things that we've noticed at A level. So when we come to think of carbon, we know that carbon has an electronic structure of 1s2, 2s2, 2p2. So you can see how the electrons have been arranged for the outer shell there. These are the ones that we can use for bonding, our second shell. We have our 4 electrons there, so our 2s orbital has been filled, and that means our other 2 electrons have gone into our 2p subshell, and they've obviously gone into separate orbitals. So if we think about how could these orbitals now form bonds, well, to form a covalent bond, each atom needs to donate 1 electron. However, this orbital is already filled. It's already got 2 electrons. So the only 2 orbitals that could actually participate in bonding are these 2. Because of course this orbital is empty, so it would not be able to donate an electron into a covalent bond. So at the moment it looks like carbon can only actually form 2 bonds, but we know that's not the case. So how does carbon get around this problem along with other atoms? Well, what carbon does is it takes its electron in the 2s subshell and it promotes it into the empty p orbital, like so. Obviously that does take a small amount of energy because the 2p subshell is higher energy than the 2s. However, the energy that will be released through bonding obviously compensates for that. So now, through doing that, we have 4 orbitals available. All orbitals have 1 electron ready to form a covalent bond with another atom. There is actually another problem when we come to look at how we could use these orbitals to bond. So we have our 4 electrons there, and they're all in separate orbitals, so they can all form covalent bonds, so far so good. But let's have a look and see what those orbitals look like. We have our 2s, which we know is spherical, and then we have the 2px, 2pz, and 2py, and they lie along the x, y, and z axes. So when we come to think about how these orbitals are arranged, we know that we have our 2px lying on this axis, our 2py is lying along this axis, and our 2pz is lying along this axis. So here I've shown 4 1s orbitals, which will represent hydrogen giving its electron. So each of these will contain 1 electron to form a covalent bond with each of these carbon orbitals. So let's have a look and see how that can do. So the first one, we will form a bond with the pz. We will also form a bond with the py orbital there, and with the px there. So we have 3 bonds, and they will all be at 90 degrees to each other because they lie along the axes there. And we now have this 4th bond, which we are going to form as well. This one will be with the 2s, which is of course spherical. Doesn't really matter where this one is, so we can pretend it's behind, or we can pretend it's somewhere else behind the other 3, perhaps at the back there. However, whatever the case is, they are certainly not the tetrahedral arrangement that we would expect and know that methane actually has. So how can we explain that one? So after promoting an electron into the 2p orbital, we are able to now mix those orbitals together. And so carbon starts with 1 2s orbital and 3 2p orbitals, and we'll mix those together to give us 4 hybrid orbitals, and we call those Sp3 hybrid orbitals because they're a mixture of an s orbital and 3 p orbitals. And you can see what those orbitals look like down in this area here. So we're just going to have a look and see why are they. You can see that one lobe is quite large. For example, on this one here, you've got quite a large orbital on that side of the nucleus and a much smaller orbital on that side of the nucleus. So why is that? Well, without going into too much detail about the nature of orbitals, um, you may have come across the fact that orbitals are in fact waves. Now, a p orbital has two lobes. So you may remember p orbital has a lobe this side of the nucleus, and then the other side of the nucleus has another lobe. And sometimes you'll see they're in different shades, and that's because they're in different phases. And you can think of this like a wave that you may have come across in physics. That the you have two different phases. You have this part which is above the x-axis, and this part which is below the x-axis. So sometimes these are called positive or negative as well, but they are in different phases. However, an s orbital, which is spherical, has only got one phase. So if this was in a positive phase that was being combined with a p orbital like this one here, over this part of axes, they would have constructive interference. So these would grow because they're both in the positive phase, whereas this part and this part would have deconstructive interference because this part is negative and this part is positive. And that's why you end up with, in this example, this lobe here getting much bigger, and this lobe becoming much smaller when you form your hybrid orbitals. So if we come and look in more detail at how these look, you can see we have our original orbitals at the top and our hybrid orbitals, four hybrid orbitals there. And when we put them together on a diagram, they actually form the shape of a tetrahedron. So you have your four sp3 hybrid orbitals that are in the shape of a tetrahedron. So we can now explain why methane has a tetrahedral shape. It's because your sp3 hybrid orbitals are in that shape of a tetrahedron, and then your hydrogen 1s orbitals, so you have four hydrogen atoms, they will come and bond with those hybrid orbitals to give you your methane molecule. We see this hybridization in obviously many other molecules as well. So we can look at water. Oxygen again has the same orbitals as carbon. The slight difference is that oxygen has 6 electrons in its outer shell. So again, your sp3 hybrid orbitals are formed, but two of those hybrid orbitals are already filled with the lone pairs of electrons which are on oxygen. So those orbitals will not participate in bonding. However, the other two will bond with the hydrogen. So that's why water has a non-linear shape because you have it's based on a tetrahedron, but two of those hybrid orbitals are occupied with lone pairs on the oxygen atom. Our final example is going to be ammonia. Again, ammonia for nitrogen, nitrogen has 5 electrons in the outer shell, so forms the four sp3 hybrid orbitals. One of those hybrid orbitals is occupied by a lone pair of electrons on the nitrogen atom. The other three are available to bond. So again, the shape of ammonia is based upon a tetrahedral arrangement of bonds. However, one of those is occupied, one of those hybrid orbitals is occupied with a lone pair, which is why the shape is called pyramidal. In further examples, we will look at other ways that we can form hybrid orbitals, but hopefully that's given you a quick introduction into how and why carbon has 4 bonds, and when it does have 4 single bonds, they're in the shape of a tetrahedron. If you would like to download these slides, if you go to the website, you'll be able to download them, and then you've got them for your own records as well.